Hi, welcome back. So today we will talk about the second part of greedy algorithms. We'll talk about Huffman codes, and this is a classical application of the so-called greedy algorithms family. Okay, so this Huffman codes algorithm is a very effective way to conduct data compression. Okay, so the input data it takes is usually a sequence of characters, and the task is to represent each character in the vocabulary, each character with a binary code, okay, of 0 and 1s. And Huffman codes, this algorithm needs to use a table of character frequencies to build up an optimal way to represent each character as a binary string. So it needs to utilize the frequency information. So in this following table, we use a very simple example to show how different ways of encoding will affect the resulting binary data, the size of the resulting binary data. So for example, we have 6 possible characters in our data, A, B, C, D, E, F, and our task is to represent each character with a binary string. And we also have the frequency information available in the first row. Okay, so this frequency information means that the character A has appeared 45,000 times in our data, and the character B has appeared 13,000 times, and so on. Okay, so in here in the third row, the fixed length code is a way to represent each character with the binary code of fixed length. And in this case, the fixed length is 3 bits. So the character A is encoded as 000, the 3 bits, and B is encoded as 001, and C is 010, and so on. So this method allocates or gives each character a fixed length of binary code, and you will find that this is not a very efficient way, because even for those very frequent characters, they are given the same the binary bits of the same size as those infrequent characters. But as you see, those frequent characters, they appears a lot of times in the data, so this is not efficient. So ideally we want the way to encoding a frequent character to be as simple as possible. So that's why we have in the fourth row of table, we have a better way of encoding or to represent each character with variable length. So the fourth row is a variable length encoding. So here the example says we just use 1 bit to encode the most frequent character A in the data, and we give 3 bits to B and 3 bits to C. And for the most infrequent character, we can give them 4. And it's kind of a trade-off, because we thought that it's okay if we give them more code because they don't appear that often in the data. Okay, so given different ways of encoding, we can compute the total number of bits for the fixed length code. Say we can use this total number of bits as a way to evaluate their efficiency. So in the third row method, in the fixed length encoding method, we can count the total number of bits by multiply the frequency with the code with the number of bits per code, right? So it's 45,000 times 3 plus 13,000, which is the frequency of B, times 3 plus 12 times 3. So that gives us roughly 300,000 bits needed in order to encode the whole data. While if we use a variable length code, for example, in the using the schema of the fourth row, we'll see that the total number of bits for this variable length code encoding is 45 times 1, because for A we only need 1 bit, plus 13 times 3, because for B we use 3 bits, and plus the rest of the products. We'll see that the total number of bits is much smaller, much lower than the total number of bits in the fixed length encoding. So this shows that different ways of encoding characters, they have different outcomes in terms of the number of bits required. Okay, so and technically we will consider this type of encoding only, so it's called prefix codes. So you consider there are two different ways of variable length encoding. Okay, so for row 3 and row 4, they are all variable length encoding, but they are kind of different because the third row is prefix code, okay, and then the fourth row is non-prefix code. And what do we mean by prefix code? So it means that no code is also a prefix code of some other code. Okay, so the code for A is 0, and 0 is not the prefix of other codes. You see, all the other codes start from 1. Okay, and the code for B, 101, is also not a prefix of other codes. Okay, so 101 only appears in the code for B, not in C or D or E or F. Okay, so this applies to all the code. So, but this is not the case for the non-prefix code. So if you look at the code for A, it's 0, and 0 also appears in the code of C, and also appears as the prefix of D, right? And the code for B is 1, and 1 also appears as the prefix for E and F. So non-prefix code has a lot of ambiguity in it. So it's hard to disambiguate different codes. Okay, so when we interpret or we decode, the prefix code is much more efficient. Okay, so during the phase of decoding, for example, decoding, the only way to decode the sequence 001, 011, 101, if we use prefix code, then the only way to decompose it is the first one, 0, represents A, and the second 0 represents another A, and then a 101 represents B, and the 1101 represents the letter E. So if it is not a prefix code encoding, right, then the 0 could be A, but the 00 could also be C according to a non-prefix code, right? So that's why we use prefix codes only, because it is most commonly used efficient way of encoding. Okay, so in order to obtain the prefix code for each characters in the data, we can use a data structure called binary tree. And it gives us a pretty convenient way to find the prefix code representation for each character. So in a binary tree, we can represent all the characters using the leaf nodes. And the code for that character is the path from the root node to the leaf node for each character. Okay, So as shown in the figures below, on the left we see a binary tree, and its root node has the value 100, and on its left branch there's code 0, and on the right branch is code 1. So if you look at the character A, it is right here as the leaf node, right? So the 45 after it is a frequency. So for the character A, its path from the root node to itself is 0. And that's why the prefix code for A is 0. And for character B, and there it is. Okay, so from the root node to character B, the path shows 1, 0, and 1. And that's why we have prefix code 101 for B. So that applies to all the characters in the leaf node here. Okay, so in the roots, in the whole binary tree here, all the characters, all the leaf nodes, they are placed into these rectangles, and all the non-leaf nodes, all the internal nodes, they are in the circle nodes. Okay, and here we also have numbers, the two integer numbers, 0 and 1, associated to the left branch and the right branch. So 0 means go to the left child, and 1 means following the branch to go to the right child. And that is a that rule applies to all the nodes in the binary tree. Okay, so if you look at all branches in each node, the left branch is always 0 and the right branch is always 1. Okay, so a binary tree should be full. So by full, I mean every non-leaf node should have 2 children. Okay, there shouldn't be empty non-leaf nodes. So the tree often, if we compare it with a tree corresponding to a fixed length code, then a fixed length code tree is not full. For example, the node here doesn't have a right branch. Okay, so this is one of the characters of binary tree for in a full binary tree for variable length encoding. Okay, so another property of a full binary tree is that if we know the size of the alphabet, okay, so if we know that in our data we have C unique characters, then the tree must have that many leaves, the size of C, the size of our vocabulary, and 1 for each character. And there are the size of C minus 1 internal nodes. Okay, so in example here we have 1, 2, 3, 4, 5, 6 leaf nodes, and 1, 2, 3, 4, 5 internal nodes in this full binary tree that correspond to the data that has 6 possible characters. Okay, and this is also another property of the full binary tree. So the problem is, the problem we want to solve is how to construct an optimal prefix code using the binary tree. Okay, so we want a optimal prefix code because we want the resulting cost of bits to be minimized. Okay, and an intuition is that we want the letters with lower frequencies should have longer paths from the roots. Okay, because a longer path means more digits or more bits in encoding that character, and because that character has lower frequency, it doesn't appear very often, so it's okay if we assign it with a longer encoding, longer code. But for those that are frequent, then we want them to be as close to the root node as possible. Okay, so the most frequent characters should be closest to the root node, because that gives us a shorter path, and a shorter path means fewer number of bits to encode that character. Okay, so in our case here, A has the lowest frequency, then it is closest to the root node. It is the direct child of the root node, while the other more infrequent characters, they are farther away from the root node. Okay, and the most infrequent characters, their distance from the root node are the farthest. Okay, so we can think about in a bottom-up way. So if we construct the binary tree using a bottom-up manner, then we should select the letters of the lowest frequency first, because those lowest frequency letters will appear at the bottom of the tree, and that means they are the farthest from the root node at the top. Okay, so we need to place the letters of the lowest frequency at the bottom. Okay, so now let's look at some other details of a tree. So a tree consists of node. So this node is the basic elements or basic units in a tree. Okay, so we consider node as those represented by the circle with the letter in it. Okay, a node has two properties, and for example, the node Z, we let Z dot left points to the left child, and Z dot right points to the right child. Okay, so we can construct a tree by assigning the node X to Z dot left, and that makes the node X the left child of Z. And by assigning Y to Z dot right, we make the node Y the right child of Z. Okay, so if we let the left child of X to be null, or the right child of V and the right child or be X, so this one should be X, also to be null, then X is a leaf node because it doesn't have a left or right child. And another frequency that we will use in Huffman Code is that each node has a property called frequency. Okay, so this frequency tells us the character, the frequency of the character that this leaf node is representing, and this frequency property can also represent the summation of the frequencies of all its children nodes. We'll see that later when we introduce the code. Now let's look at the pseudocode of Huffman Code algorithm. Okay, so this procedure called Huffman takes inputs a variable C, and this parameter C is the set of n characters that we want to encode. Okay, and line 1 compute the size of the vocabulary, like how many unique characters are there. Okay, and line 2, it is, and also besides the character in each character in the vocabulary has a frequency attributes. Okay, we know the frequency for each characters. Okay, and at line 2, this line initialize a minimal priority queue. Okay, it is a special data structure that we will need to use. So by the name minimal priority queue, you might have recalled that we have something similar to a max priority queue, or something similar in the previous lectures. So this queue data structure can be implemented by the heap data structure that we have talked about before. Okay, so this minimal priority queue, it's similar to a queue, and in the queue, the elements that first get in will get served first, right? And if it's a priority queue, then we will assign a priority score to each element in the queue. So the elements with the highest priority score will get served first. And then in the minimal priority queue, the elements with the minimal value will have the highest priority. Okay, so this special type of data structure can be implemented using a node data structure like minimal heap. Okay, so in a minimal heap, the root node is always the elements that has the minimum value, has the smallest value. Okay, so a minimal priority queue supports a lot of operations, and extract min of queue is one of it. So this operation pops out the smallest element. Okay, it gets the smallest element and it pops it out. Okay, so at line 5, line 7, we have two calls of extract min, and finally at line 11, we also return the element that has been popped out. And it also supports operations like insert. Okay, so in line 10, we insert a new node into the minimal priority queue, and the resulting of insert z is that z will be in the correct position in it. It's not like randomly insert. It will need to find the correct position to insert and then insert a new node. So having a look of this algorithm, we can see that it is just one for loop, and the for loop ranges from 1 to n-1, and within each iteration we will allocate a new node z, and we first extract the minimal elements from the queue, which is x, and we make x the left node of z, and then we extract another minimal elements from Q, which is y, and then we make y the right node of z. Okay, so basically from line 4 to line 8, we extract the two smallest elements in the minimal priority queue and make them the left and right child of the new node z. And at line 9, we makes the frequency components or frequency property of the new node z to be the summation of the frequencies of x and y. Okay, so z at the top, the frequency of it is a summation of the frequency of its children. And lastly, at the end of this iteration, we will insert the z back into the queue. Okay, but this time the new node is not x nor y, but the new node z, which has a summation of their frequencies. So that means z will be in a different position than x and y. Okay, so that's the pseudocode of the Huffman code, and let's see how it works with a simple example. Okay, so if q is initialized like this, okay, we have 6 possible characters associated with their frequencies. Okay, so q is initialized like this. So it's in an increasing order because q has is the minimal priority queue that the elements with the lowest values will with the lowest frequencies will be served at first. Okay, so F is at the front. Okay, so within the iteration of the for loop, we will first pop out one node with the minimal value, which is the letter F with frequency 5, right? And we will pop out another element, which is the letter E with frequency 9. And what we do is to make a new node Z with F as its left child and the letter E as its right child. Okay? And the frequency of Z to be the summation of both. So that means we created some node like this. Z is at the top, on the left is F, and on the right is E. And we know that the left branch represents 0 and the right branch represents 1. Okay? So the next step is to insert this new node Z back to the minimal priority queue. Okay? So because this new node Z has a frequency 14, which is summation of 5 and 9, so it will be in the position right after B, because B has a frequency 13 and the D has a frequency 16, so Z will be here. Okay, so that's the results after the first iteration of the for loop. Okay, so beginning the next for loop, we'll do the same thing. We will extract the current minimal node, the current element with the minimal priority, with the minimal frequency, which is the node C, right, with the letter C with frequency 12, and we extract another minimal node with frequency 13, which is letter B. And what we do is to make another Z node that use C as its left child and the B as its right child. Okay, and then insert it back into the queue, which will be like this. Okay, so after the second for loop, a new Z node will be inserted into the queue. It has a summation of frequency, which is 25. It's 12 plus 13, right? So that's why the new Z will be here. Okay, so let's begin the third third iteration of the for loop. So it's a bit tricky now, because when we extract the minimal node from the queue, it is this combined node that will be extracted. This new node has a frequency 14, so it will be popped out. Okay, so this new node will be popped out. And the second node being popped out is D. It has 16. So what we do is to create a new node and make this orange node its left child and make D its right child. Okay, so you see the orange node with 14 as its frequency will become the left child of this new node, and the D will be the right child of this new node. Okay, so it's a hierarchical structure here, and the new node has a frequency which is a summation of 14 and 16. Okay, and then having this new node, we need to insert the node 30 back to the queue. Okay, which results this structure in our minimal priority queue. So 25 is the first node now, and the 30 is the second node, and the A is the last node. Okay, so the next iteration is also straightforward. We'll extract the node, pops out the node 25, right, and pops out the second node 30, in the blue color. So this whole thing will also pop out, and then we make a new node with the orange node as its left child and the blue node as a right child, and on top of it is its parent node is the new node that has new frequency as 55. Okay, and please note that on each branch there's a number associated to it, because we know that the left child represents 0 and the right child represents 1. Okay, so and before the iteration ends, we also need to insert this very big node back to the queue. Okay, so the result is that we have only 2 nodes in this queue, right? And A is the lower is a node with a higher priority because it has lower frequency. So in this last iteration, we need to pop out these 2 and make a new node, right? And then insert back into the queue again. Okay, and this frequency has a summation of 100. So this will be the last node in the queue. So the last line of Huffman code will pop out the only node in the queue, which gives us a binary tree. And this binary tree is just the result, exactly the result we want, because it contains the optimal prefix code for all the characters in it. Okay, and if we examine the results a little bit, and it gives us that the character A has a code 0, and the character B has a code 101, and C has a code 101, 100, and D has a code 111, and E is 1101, and F is 1100. Okay, so it is a prefix. It is a optimal prefix code. Okay, so our textbook proves that why this algorithm is correct, why it produces some optimal prefix code. So it's not required to understand the proof, but all we need to know is that the Huffman code algorithm will generate some prefix code, and this prefix code is optimal because it assigns the longer path to the less frequent character and the shorter path to the most frequent character in it. Okay. So now let's look at look at the question of why we put Huffman code as one of the greedy algorithms. That is also a quite an easy property to find, because we want to minimize something. We want to minimize the total cost of bits to encode a file. Okay, and the total cost can be computed by the summation of products between the frequency of character and its depth in the tree. Okay, and we will never know the total cost unless we finish the tree, unless we completely build the tree. Okay, so but when we construct the tree from bottom up, right, we do not know what the resulting tree would be when we are choosing the current nodes. All we need to know is to make the locally best choice. Right? So all we need to do is to choose the node that has the larger path at the beginning. Okay? So choosing the current 2 nodes with the lowest frequency will minimize the cost of the current step. But in theory, we don't know if minimizing the current step will result in the global minimized results. right? So we don't know that yet. So this is where the greedy choice happens, and that's why this Huffman Code algorithm is counted as a greedy algorithm. Okay, so lastly, let's look at the running time of Huffman Code algorithm, and it's also quite easy to conduct because we have one for loop, right? It has n-1 iteration, and within one iteration of the for loop, we have two pop out operation and one insert operation on top of the minimal priority queue. Okay, so these types of operation, if we want to know their running time, we want to know their efficiency, right? So if we implement a minimal priority queue with some data structure like minimal heap, then these types of operations like extract min or insert, they all take the logarithm of n times. So it's quite similar to the max heapify operation that we have defined for the heap sort. Okay, so that's why the total running time is big O of n times logarithm of n. Okay, because at each iteration we have logarithm of n times, and we have n such iterations. So it's a quite efficient algorithm. Its running speed is similar to a sorting algorithm. Okay. So here let's have a bit recap of the basic elements of greedy algorithms. So in order to implement a greedy, to take a greedy algorithm, to take a greedy approach, we need to have a greedy choice which can be used to help us to achieve a global optimal solution. Okay, so by making a locally optimal greedy choices, we can reach a globally optimal solution. Okay, and basically we're making a choice that's seemingly to be the best for the current problem, but in fact we don't actually consider the results from, we're not considering the results from all the subproblem space. And optimal substructure is also another element for using greedy algorithms to solve problems. So it is similar to the condition of dynamic programming. We also like the problem to the solution to the original problem to contain the optimal solutions to subproblems. Okay, but the difference from dynamic programming is that we don't need to solve all the subproblems, and we just need to make a greedy choice in the original problem, and so that means we just solve one subproblem from the splitting. So after we decompose the original problem into several subproblems, we don't solve all of them. We just choose to solve one of them based on the greedy strategy. So next parts, we're gonna show the connection between greedy algorithms and the dynamic programming using this specific example of knapsack problem. There are two types of knapsack problems. So the first type is called ZeroOne Knapsack, or discrete knapsack problem. So this problem says, imagine a thief robbing a store. He finds n items, and the ith item is worth VI dollars and weighs WI pounds. Okay, so VI and WI are all integer numbers for simplicity. And he can carry at most capital W, which is also an integer pounds, in his knapsack. So his goal is to maximize the value of all the items within his knapsack. So which items should he take? So it's a bit like a constrained optimization problem, and his constraint is that he has the capacity of his knapsack, which is W, and he can and also each item has also a discrete number of weights. Okay, so for example, if there are 3 items in total, and item 1 weighs 10 pounds and it's worth $60. The second item weighs 20 pounds and is worth $100. And the third item weighs 30 pounds and is worth $120. And his capacity of knapsack is 50 pounds. So which items should he take? Okay, so this is a simple example, so we can enumerate over all possible combinations. So what if he takes item 1 and 2, which takes 30 pounds in total, and there are only 20 pounds space left, so he cannot take item 3 with them. So the total value of the 2 items is 100 plus 60, and which is $160. A second option is he takes item 1 and item 3, okay, which takes up to 40 pounds, and the total value is $180. And what if he takes item 2 and item 3? Then the total space is filled, right? 50 pounds in total, and the total value is $120 and $100, which is $220. Okay. So it looks easy using this simple example, but this is not a easy question, because if you have a lot of items, a lot of different combinations, and sometimes you need to make the trade-off between the heavy items versus the heavy items versus the valuable versus less valuable items. So this is a typical problem that can be solved by dynamic programming, because after you take some item, right? So for example, you have 50 capacity. After you take the item 1 first, your capacity decreases from 50 to 40. So the remaining problem is a smaller instance of the original subproblem, So the subproblem is given a capacity of 40 pounds, and the available items are item 2 and item 3, right? So this is a similar but smaller subproblem. Okay, so in order to get the optimal solution, you need to solve all subproblems, but you should use dynamic programming without solving the same problem repeatedly. Okay, and there's a second type of knapsack problem, which is a fractional knapsack or continuous knapsack problem. So in this case, we have the same setup, but the thief can take fractions of items rather than having to make a yes or no choice on each item, right? He can take part of the item 1 or part of item 2, and he can decide how much fractions of the item he wants to take. So this small change makes the nature of the problem different. Okay, so this problem we don't need to use dynamic programming, but we can solve it by simply using a greedy strategy. Okay, the idea is that we can pick the most valuable item by computing or calculating the unit price for each item. So the problem tells us that the item I has the value Vi and the total weight of Vw WI. So we can use VI divided by WI to compute the rate or the unit price for that item. And we just pick the most valuable item that has the highest rate or highest unit price. Okay, so in this case, we have the same input, right? And by computing the unit price, we found that item 1, the unit price for item 1 is 6. So per pound has $6, is worth $6 for item 1. And for item 2, the unit price is 5. And for item 3, the unit price is 4. So according to this strategy, item 1 is the most valuable item we should first consider, right? The thief should first consider. So the optimal solution is that we take as much item 1 as possible. So we take all the items in it and all the item 2 in it as well. As for the remaining space, so we have 20 pounds remaining, right? So we take 2/3 of the item 3. So that gives us 80 more. So if we are allowed to take fractions of items, these will certainly be the optimal solutions. And the greedy strategy will give us this optimal solution. So hope this example show you the connection between dynamic programming and greedy algorithms. So it really depends on how the problem is framed, and you can we also made similar comparisons in the activity selection problem, right? So we found that using dynamic programming approach, we can also solve the activity selection problem, but it's an overkill, which means we don't need to solve all the subproblems. And by adapting some strategy, some greedy strategy, we can also obtain a rich solution. Okay, so I guess that's it for this chapter of greedy algorithms. And if you have any questions, you can always drop me emails, and or you can visit my Zoom conference room during the office hours. Bye bye.